Welcome to another deep dive. Today, we're going to be exploring something pretty mind-bending, quantum mechanics.
That's right.
But don't worry, we're not going to be like, uh, you know, diving into complex equations or anything.
Yeah.
We're using this really fascinating essay by Yergo Schneepat as our, jumping off point.
Shoo.
And he does a great job of explaining, these pretty complex concepts in a way that, anybody can grasp.
Absolutely. It's a great starting point to kind of delve into this world.
Yeah, so we're going to be talking about things like, particles acting like waves,
Uh,
the mystery of Schrödinger's
Give
cat,
infamous cat.
and even how quantum mechanics is already shaping the technology that
Yeah.
we use every single day.
Yeah. I mean, it really is the foundation for a lot of our modern technologies.
Exactly, exactly. So to get us started, Schneepat takes us back to the early 20th century. Back then, physicists, they thought they had it all figured out. They had their classical physics laws, and they thought, hey, we've got the universe pretty much nailed down.
It's all very clockwork, right? Yeah.
Exactly. It's like, we've got this. But then they started to notice these things that just didn't fit with those neat and tidy laws. Like one of those things was black body radiation.
Oh, yeah.
So basically, objects weren't emitting energy the way classical physics said they should. And it was a real head scratcher for them. Like, what's
Yeah.
going on here?
Yeah. It was one of those moments where they were like, uh-oh, something's not quite right with our understanding.
Yeah. And this is really where the whole quantum revolution kind of started brewing. So one of the big problems they were wrestling with was this thing called the ultraviolet catastrophe.
Ah, yes, the ultraviolet
Oh,
catastrophe.
yeah. So, I mean, it sounds pretty dramatic, right? And for good reason.
Right.
So classical physics was basically predicting that objects should emit an infinite amount of energy at high frequencies.
Yeah. Yeah. Which would be not great for us.
Not great at all.
Yeah.
Yeah, we'd all be, fried to a crisp.
Yeah.
But clearly that wasn't happening.
Thankfully not.
Thankfully not. Right. So it's like, okay, something's got to give.
Right. The theory needed some tweaking.
Yeah, exactly.
Uh,
So along comes this guy, Max Planck, and he basically throws a wrench in the whole system.
yeah, he throws a big wrench in it.
He comes up with this radical idea. He's like, hey, what if energy isn't continuous? What if it comes in these tiny little packets, like discrete bundles of energy?
Oh, bundles.
Yeah,
Yeah.
little bundles. And he called these packets quanta.
Quanta. Yes.
And it's like, imagine instead of having a ramp, you have a staircase.
yeah, that's a good analogy.
You can only go up or down in these specific steps, these specific amounts of energy.
Exactly. It's quantized.
Right. Quantized. And this idea, this was huge. This introduced the concept of quantization, which basically means, like you said, that energy exists in these discrete units. It's not this smooth, continuous spectrum.
And it also led to the discovery of a fundamental constant, a Planck's constant,
Right.
which governs the scale of these energy packets. And it's one of the most important constants in physics today.
Totally, totally. So Planck kind of lays down this groundbreaking idea. And just a few years later, who enters the scene? Einstein,
Of course, Einstein.
the rock star of physics. He comes along and he's like, hey, I'm going to use this quantum idea that Planck came up with to explain something called the photoelectric effect.
Yeah, the photoelectric effect.
Yeah.
Which is, well,
Yeah, it's basically how light shining on metal can knock electrons loose.
right. It can cause electrons to be emitted.
Right,
And that was a big deal because it showed that light itself, which people thought was just a wave,
right.
it also behaved like a stream of particles,
Yeah.
what we call photons now. And this is where we get the whole wave-particle duality thing.
Oh my gosh. So light can be both a wave and a particle.
Yeah, depending on how you're looking at it, how you're measuring it.
Oh, that's trippy.
It's one of the most mind-bending concepts in quantum mechanics.
And it was like just the beginning of things getting really weird in the quantum world.
Yeah. It challenged the very foundations of classical physics.
Hmm.
Around the same time, we have Niels Bohr, who was working on a new model of the atom,
Right. Bohr's atomic model.
building on the work of Ernest Rutherford, who had discovered the nucleus, but Bohr kind of added the quantum twist to it.
Right. Rutherford had discovered the nucleus, but it was Bohr who kind of took it a step further and really incorporated these quantum ideas into the model of the atom.
Yeah. He proposed that the electrons in an atom, they can only occupy certain energy levels.
Right.
Kind of like they're restricted to specific orbits around the nucleus. Like they can't just be anywhere they want.
So it's like there's these these specific allowed orbits or shells for the electrons.
Exactly. And the really interesting part is Bohr explained that when an electron jumps between these energy levels, it either absorbs or emits a photon of light
A photon of light,
with a very specific energy.
right?
And this helps explain why different elements, when you heat them up, they emit those characteristic colors. Because each element has its own unique set of energy levels.
Oh, that's so cool. So it's like each element has its own fingerprint, but it's a fingerprint of light based on these quantum jumps.
Exactly, a spectral fingerprint. And this was a huge step forward in our understanding of how atoms work.
So we're starting to see how these like seemingly abstract quantum ideas actually explain things that we can observe in the real world.
Yeah, absolutely.
But then things get even wilder, right?
Oh, yeah.
With Werner Heisenberg and his famous uncertainty principle, Schneppat spends a good amount of time on this.
Yeah, he really delves into it because it's so crucial to understanding how different quantum mechanics is from classical physics.
Right, totally. So Heisenberg basically says you can't precisely know both the position and the momentum of a particle at the same time.
You can't know both with perfect accuracy,
Right.
and the more you know about one, the less you know about the other.
Yeah. It's like, imagine trying to pinpoint the location of like a tiny little super fast moving particle. Like, how would you even do that?
Yeah. It's nearly impossible.
Right. Because the very act of measuring its position would mess with its momentum.
Absolutely. Because you'd have to interact with it somehow to measure it.
Right. And vice versa. If you try to measure its momentum, you mess with its position.
It's like trying to nail down a soap bubble.
Oh, yeah. It's a perfect analogy.
The moment you touch it, it pops or it changes shape. It's inherently slippery.
Right. It makes you wonder, like, what does it even mean to know something at that level?
It really does challenge your classical intuitions.
Yeah.
Heisenberg's uncertainty principle was a radical departure from the deterministic worldview of classical physics. It introduced this idea that probability and chance, they're not just limitations in our measurement abilities. They're fundamental aspects of reality at the subatomic level.
So we're dealing with a whole new ballgame here. It's not just that our instruments are imperfect.
Right.
It's that there's this fundamental limit to what we can know about the universe. So where do we go from there? Like, if we can't precisely know a particle's position and momentum, how do we even begin to describe it?
Well, that's where Erwin Schrödinger comes in with his wave mechanics.
Yeah, Schrödinger developed this mathematical equation,
Yeah.
that describes quantum systems not as particles, but as waves. Remember that whole wave-particle duality we were talking about?
Oh, yeah.
Well, now even particles have a wave nature, you see.
Okay, so we have to think about, like, electrons and all those other tiny things, not as, like, little balls, but as waves.
Exact.
But what kind of waves are we talking about here? It's not like they're surfing on the ocean.
Right.
Yeah.
Good point. It's not a physical wave like a water wave. It's more of a mathematical wave.
Oh.
It's a way to represent the probability of finding a particle in a particular place at a particular time.
Probability, huh?
Yeah. So this wave function, that's what we call it, this wave function, it basically encapsulates all the information we can possibly know about a quantum system. Okay, I think I'm starting to get it. So instead of knowing exactly where a particle is, we have this wave function that tells us like the likelihood of finding it in different locations.
Exactly. It's like a map of possibilities rather than a fixed point on a map.
Oh, okay, I like that. A map of possibilities. That's a good way to think about it.
Yeah, and Schrödinger's wave mechanics, it provided this really powerful tool, to describe and predict the behavior of quantum systems. But it also led to some pretty heated debates, let me tell you. I mean, there were some real arguments among physicists about how to interpret quantum mechanics.
Oh, yeah, like what?
Well, one of the most famous interpretations, and the one that Schneppat really focuses on in his essay, is the Copenhagen interpretation.
The Copenhagen interpretation.
Yeah, well, you've probably heard of it.
I've definitely heard the name, but I'm not sure I totally understand it. What's the main idea there?
So the Copenhagen interpretation, which was, championed by Niels Bohr and Werner Heisenberg, these big names in quantum mechanics, right?
Right.
It suggests that quantum properties, they aren't actually fixed until they're measured.
What? You're saying that things are like fuzzy and undefined until we actually look at them?
That's basically the gist of it. It's kind of like saying the act of observation actually influences the reality of the quantum world.
Hold on a second. Are we saying that reality itself depends on whether or not we're looking at it?
That's a big question. A lot of people interpret it that way.
That's a wild concept.
It is pretty wild. It's like, imagine a coin. Right, flipping in the air.
Yeah, yeah.
In the classical world, we know it's either heads or tails, even when we're not looking at it.
Right.
Yeah.
That makes sense.
But in the quantum world, according to the Copenhagen interpretation, it's like that coin, it's in this weird state, a superposition, where it's both heads and tails at the same time until we actually stop it and look at it.
Hmm.
And then that active observation, that's what forces it to choose one state or the other.
So it's like reality is this blurry mess until we actually observe it, and then it kind of snaps into focus.
Yeah. Kind of, yeah. And that's why Einstein wasn't exactly thrilled with this idea.
Einstein wasn't on board. What did he think about all this?
Well, Einstein, he believed in a deterministic universe. He famously said God does not play dice, meaning he thought there had to be some underlying order to the universe, some hidden variables that we haven't discovered yet that would explain this apparent randomness.
So he didn't like the idea that things were just random and probabilistic at the fundamental level.
Exactly. He thought there had to be a better explanation. And this disagreement between Einstein and the proponents of the Copenhagen interpretation led to some pretty interesting debates and thought experiments. Have you ever heard of the EPR paradox?
The EPR paradox. I feel like I've heard that somewhere.
Yeah, it's named after Einstein and his collaborators, Boris Podolsky and Nathan Rosen. They came up with this thought experiment to kind of challenge the completeness of quantum mechanics.
Okay, what's the paradox?
Well, it involves this thing called entanglement.
Entanglement.
Yeah, where two particles are kind of linked together in this weird way, right? Their fates are intertwined even if they're separated by huge distances.
Okay, so if you measure one entangled particle, you automatically know something about the other one, even if they're light years apart.
Yeah, that's the basic idea. And it's like, how do they know about each other if they're so far away? It's like they're communicating faster than the speed of light, which Einstein said was impossible. So the EPR paradox, it's like saying either quantum mechanics is missing something or this spooky action at a distance is real.
Spooky action at a distance. I like that. It definitely sounds spooky.
It really does. It challenges our basic intuitions about how the world works. And Schneppat does a great job of explaining this in his essay. He also talks about another thought experiment, one you've probably heard of, that really captures this weirdness of quantum mechanics, Schrödinger's cat.
Ah, yes, the cat in the box. I have heard about that one, but I'm not sure I fully get it.
Yeah, Schrödinger's cat. It's not really about cats, It's more about highlighting how bizarre it would be if the principles of quantum mechanics, which we usually think of as applying to the microscopic world, if we applied them to everyday objects, like, a cat.
Okay, so walk me through it. What's the deal with this cat?
All right, so picture this. You've got a cat, right, stuck in a box.
Poor cat.
Yeah, not a great situation for the cat. But inside the box, there's this contraption, right? And this contraption, it's got a radioactive atom that has a 50-50 chance of decaying within, let's say, an hour.
Okay.
So if that atom decays, it triggers this mechanism that releases poison gas, killing the cat. But if it doesn't decay, the cat's fine.
So it's like a 50-50 chance the cat survives.
Exactly. Now, here's where the quantum mechanics comes in. Until we open that box and observe the cat, according to the Copenhagen interpretation, it's in this superposition of being both alive and dead.
Wait, are you serious? The cat is both alive and dead at the same time? That doesn't make any sense.
That was Schrödinger's point. He was trying to show how ridiculous it would be if we applied the rules of the quantum world to our everyday world. The Copenhagen interpretation says that it's the act of observation that collapses the wave function, forcing the cat to be either alive or dead. But until that observation happens, the cat exists in this limbo of both possibilities.
That is some seriously mind-bending stuff. It all sounds very theoretical. Did all this debate about the Copenhagen interpretation and the meaning of quantum mechanics, did it actually lead to any practical applications? Did it have any impact on technology or anything like that?
It did. It really did. I mean, all this quantum weirdness, it wasn't just some theoretical stuff that physicists were, arguing about in their ivory towers. It actually had some real-world implications. Schneppat emphasizes this, too, in his essay. It led to some of the most transformative technologies of the 20th century.
Really? Like what?
Well, think about transistors, the tiny little things that are the building blocks of all our modern electronics.
Okay, yeah.
Computers, smartphones, all that stuff. They rely on a quantum phenomenon called tunneling.
Tunneling.
Yeah, where a particle can pass through a barrier that it shouldn't be able to, according to classical physics.
Oh, wow. So are you saying, my smartphone is basically a quantum device?
In a way, yeah. It's using quantum mechanics to function, and that's just the beginning. What about all those futuristic technologies we keep hearing about, like quantum computers? Schneepat mentions those too.
Yeah, quantum computers, those sound pretty mind-blowing. Are those actually going to happen?
Oh, absolutely. Quantum computers are one of the most exciting frontiers of quantum technology, and they harness these principles of superposition and entanglement that we were talking about earlier to perform calculations in ways that classical computers, the ones we use now, just can't.
Okay, remind me again, what's superposition?
So, remember how we talked about how a quantum system can be in multiple states at once? Like that coin being both heads and tails at the same time?
Oh, yeah, right.
Well, quantum computers, instead of using bits, which can be either 0 or 1, they use these things called qubits.
Qubits. Oh,
In qubits, they can be in a superposition of both 0 and 1 at the same time.
so they're like super bits.
Yeah. And this allows quantum computers to perform multiple calculations simultaneously, giving them this massive speed advantage for certain types of problems.
So it's like having a computer that could explore like a million different paths at once instead of just one at a time.
Exactly. And this ability to exploit quantum phenomena, it means that quantum computers can potentially tackle problems that are impossible for even the most powerful classical computers we have today, like breaking encryption codes or simulating complex molecules for drug discovery.
Wow, so this is like next level computing power.
It really is. It's a game changer.
Schneepat mentions another application, quantum cryptography. What is that all about?
Well, quantum cryptography uses the principles of quantum mechanics to create like super secure communication.
Super secret.
Yeah, basically unbreakable, because any attempt to eavesdrop on a quantum communication channel, it would inevitably disturb the quantum state, right?
So you couldn't sneak a peek without getting caught.
Exactly. You'd be busted. So the sender and receiver would immediately know if someone was trying to listen in.
It's like having a built-in security system that's based on the laws of physics themselves.
That's a great way to put it. And it's not just science fiction anymore. There's this thing called quantum key distribution, or QKD for short,
UK
where secret keys are encoded in photons, those little particles of light, right?
Yeah.
And any attempts to intercept those photons would alter their state, making eavesdropping basically impossible.
That's amazing. What about quantum sensors? I've heard of those too.
Quantum sensors, those are incredible. They use the extreme sensitivity of quantum systems to measure physical quantities like magnetic fields, gravitational waves, even time itself with incredible precision.
So we could use these sensors for all sorts of things like navigation, medical imaging, even like scientific research.
You got it. They have the potential to revolutionize so many fields, from medicine and material science to environmental monitoring and space exploration.
It's mind-blowing to think that all this started with a few physicists just trying to figure out some strange things about light and energy. Schneepat's essay does a great job of tracing that whole journey,
Yeah.
from those early puzzles to these incredible technological breakthroughs.
It really does. It shows how these seemingly abstract ideas about quantum mechanics have had such a profound impact on our world.
Yeah, it's a real testament to the power of human curiosity, and the drive to understand the universe. And Schneepat leaves us with this really thought-provoking question, I thought.
Oh, yeah. What's that?
If, as quantum mechanics seems to suggest it, the act of observation can actually influence reality at the subatomic level,
Right.
what does that mean for us? For our understanding of the universe and our place in it?
It's a deep question. It makes you wonder about the nature of reality itself.
It's like it challenges our whole way of thinking about what's real and how we perceive the world.
Yeah, and it's a question that philosophers and physicists are still debating today. And, one thing's for sure, the quantum revolution, it's not over. I think we're just scratching the surface of what's possible. As we keep exploring this strange and counterintuitive world of quantum mechanics, who knows what other amazing discoveries we'll make.
It's exciting to think about. That was quite a deep dive. Quantum mechanics, it's definitely one of the most fascinating and mind-boggling fields out there.
Mhm.
And it just goes to show that we're constantly learning new things about the universe. And the more we learn, the more we realize how much we still don't know.
It's a humbling and inspiring thought.
It is. And who knows, maybe one of our listeners out there will be inspired to make the next big breakthrough in quantum mechanics.
That would be amazing.
It would be. Well, thanks for joining us on this journey into the quantum realm. We hope you enjoyed it. And until next time, keep those brains buzzing.
Keep exploring.
Keep questioning.